Okay, welcome to the class. In the last class, I told you that these molecules or cryptands, there are two aspects of their synthesis. One is called strategy and the other is methodology, right. One is strategy and the other is methodology. And I discussed about there are four strategies of synthesizing these molecules, starting from non-cyclic starting materials. So, about the methodology, two aspects. About the methodology, I will tell you the first is template method. Template method template method. Okay, this is the first method I will describe and I will tell you in terms of a story. Okay. We wanted to make this, I said that we introduced first the tripodal coupling, that is tripod and two tripods will come. Okay. So, now why they will come? We have to put a template, so that the template will bind template because they are far apart. So, if I put a template, maybe I will write the, if I put a template, all right. If I put a template, I am writing template as a metal ion. So, I am writing like this, this is my template, fine. So, if I put a template, then both of them will come together, both these tripods, template will bring them together. So, template will come here and they will react. When they are close, they will react and I will get the desired cryptand. So, this was the idea. So, with this idea, we made this starting material can be made. I am not telling you how to make it and all that. These are available in books and all that, but suppose it is not very difficult to make. Okay. This compound is available in the market, Aldrich sells it and so many other companies sells it, NH2, okay. And this is called tris 2-aminoethylamine. In short, it is called TREN. And the other one that we made was like this. Okay, I will write here only. It will be easy for me to write. It is easy for me to write. Where is it? Yeah. That's why 1, 2, 3, 1, 2, 3 oxygen and this and then CHO CHO and CHO. Okay, this trialdehyde, we call it trialdehyde. So, now why they will meet? They will meet because I will use a metal ion as template, followed. So, metal ion as template, we expected that this will come like this, and then it will come let me draw like this. And then amine and aldehyde will combine to form a C base. They will form a C base, double bond, then okay, and here also it's not, I lost it. Maybe on this side I will put, it will be easier. So, it will form a C base like that, and then upon reduction it will form the, upon reduction what will happen? I will make this particular compound. NH, NH, no, it is immediately, I made mistake. And the third one is also, let me finish it with cartoon. So, this was our idea. So, for 2 years we struggled with, usually people take, when they take template, they usually people take transition metal ions. So, used to take all first row transition metal ions, second row transition metal ions and try this reaction, and this reaction never got success. Then suddenly one bright morning we decided to start using alkali metal, and precisely we tried with cesium chloride. Cesium chloride has some solubility in methanol. Large quantity of methanol we took and we put cesium chloride and it worked very well. We got 40% yield. Why was that? That is, you have to know this reaction. CHO, okay, and then NH2, then R, say R prime. If they react, how they react with aldehyde? They react like this. Typical reaction, that it will go there and then the lone pair will attack the carbon to form the imine. From the imine I will get amine, and then I will get a stable cryptand. So, that means it depends upon the availability of the lone pair on nitrogen for the reaction to go forward. The reaction did not go forward. Why? Because we took always a transition metal ion, and a transition metal ion binds with this amine pretty well. That means binds pretty well, it binds, that means the lone pair is not available further for attacking this carbonyl carbon. So, reaction did not go. Therefore, when we took alkali metal ions, it binds this both oxygen and nitrogen, but very weakly. But what it does, it brings the two part, one part and second part, two parts together like this. So, cesium will bring, cesium plus will bring them, and it will go very nicely to imine. From imine it will go to amine, and we got our product. Okay? Almost 40% yield, which was tremendous. So, since then it is very, when you use template, all this story is to tell you that when you use template, and especially metal ion as a template, you should be very, very careful which metal ion you are taking and what reaction you desire. So, with that idea, your choice of template should be very, very good, so that the reaction go pretty well under the influence of that metal ion. So, with transition metal this does not work at all, but with alkali metal ion it works perfect, and we get the cryptand in about 40% yield, that can be crystallized as a bright colorless crystals like sugar cubes. You have taken this, you have seen sugar, okay, big particle sugar, single crystals. So, here also you get single crystals, and we did the X-ray structure of that. So, that is template method. So, just remember, when you use template method, we must choose a metal ion properly. After that, high dilution method. After template, there is another method called high dilution method. If you high dilution method, high dilution method. As I told you earlier also, when we discussed synthesis of macrocycles, high dilution means the intermediate has enough residence time in the mixture, so that it can undergo desired intramolecular condensation, okay, intramolecular, not intermolecular. So, to make intramolecular, we have to take high dilution, and high dilution, as I told you earlier during macrocyclic synthesis, macrocycle synthesis, that high dilution means it will go for days, sometimes more than 1 week it will go. So, those things you have to remember. After that, another new method. So, this is second method, high dilution, and we very cleverly made this high dilution. How I am going to tell right now. What happens is, this trialdehyde that I told you, that I have written here, that trialdehyde, I am doing cartoon now because otherwise it will take a long time. This trialdehyde is not that much soluble in methanol, especially at room temperature. Okay. So, when we take it in the solution phase, then then concentration of this trialdehyde is very small, and then from top we put this train, dropwise, a dilute solution of train dropwise. That means, what you have in solution, you have very small amount of this trialdehyde, and we put a very dilute solution of amine from top, that too dropwise, and that not as slow as high dilution technique, but here we generate the situation of a high dilution by playing with solubility. So, here we do that, and dropwise it falls, and then we can get a very good yield of this product. This can be done then without using a template. While we are playing with this, then one group from US, they showed that they made this compound. I am showing you NH2 train, then glyoxal, this is glyoxal, is better to use cartoons, we can easily illustrate. So, they took glyoxal, dropwise falling glyoxal in methanolic solution, and we have a train, whole thing, their temperature, they did not do it at room temperature, but they did keeping the temperature around 5 degrees Celsius. Okay. So, you can easily keep this at 5 degrees Celsius without using any templating ion, and you see that there are 12 points, at 12 reactions will go on the same time, 1, 2, 3, 4, 5, 6, and then 6 means there are 12 units, they have to bind like this. So, at 5 degrees Celsius they got a very high yield. So, there is another method that is low temperature method. And why it worked, I will tell you now. Low temperature method. So, low temperature, in low temperature method, what happens, this amine, let me put, suppose this I am taking care of this amine, this amine at room temperature, if you put in a solution, this amine is playing all these three arms, but you lower the temperature, degrees of freedom of movement of these three will be drastically reduced. If you put the temperature at low, at 5 degree around, then this amine will not roam around, but they will be they will still roam around, but they will be almost fixed in one position, because the temperature is so low, they will not fix their room temperature, they are doing this, but when the temperature is low, they will be like this, and that is why two are coming this way and the glyoxal is linear. So, it is immediately binding, we are getting high yield. So, low temperature is another very important method. Therefore, in the methodology that we have discussed thus far will be using a template number one, and as I told you, template, the metal ion must be chosen properly, judiciously, with lot of thinking should go into choosing a particular metal ion. Number two will be high dilution, but high dilution has its own problem, because it requires lots of solvent. So, you have to recycle the solvent, otherwise you will waste lot of chemicals. Okay. And then another method that we use nowadays is the low temperature method. So, the best method might be, you can take a low temperature and a template as well, that is what we do. You take a metal ion as a template, particular metal ion as a template, and use low temperature. So, both, when you take both, then sometimes we can get the yield as much as 90%. If you tell somebody that some reaction like this, we got 90% yield, he will laugh at us, because it is impossible. But indeed, if you take a good templating ion at say 5 degree Celsius, it is possible to get 90% yield. So, these are the two aspects of synthesis that I talked about. One was the strategy and the other is methodology. The 90% yield was, I will tell you now, I will show you the picture. It will take some time, but nevertheless let me show it before I end. So, pyrazole Okay. So, we made this compound. I am drawing the other two bridges identical. So, I am writing here, writing like this to save time. See that? So, this is a cryptand having a very long cavity, and this is you can obtain at low temperature. With this we did not use any templating metal ion, but at low temperature we used. And what did we use? We used this aldehyde. So, this is an aldehyde, dialdehyde. Okay, this is dialdehyde, and we acted with this. So, we got this particular cryptand at 90% yield. So, in some cases really wonders can happen with this kind of molecules. Okay, so, that is probably ending the class today. So, therefore, I told you that synthesis of this compound and how some of these structures are. Now, I will tell you their complexing abilities. So, there can be monomeric. Okay. I will now use, I will always use cartoon now, otherwise it will take a very long time. But I will one day I will write all the references for you to follow. Okay. So, you can take monone. We already discussed about these donor. When you have nitrogen donors, they are they are preferred by transition metals. So, if you take a say copper, then what will happen? Copper will go here. Copper will be here, copper binds here. Okay, it binds to these nitrogens. Okay, 1, 2, 3, 4. So, 4 nitrogens binds to this copper, and its other here is empty. This part is empty, there is nothing. So, that something can come and do some chemistry also. That chemistry I will show you another day. So, what happens is it comes and something can bind here, something can bind here, some organic moiety, and then another can come here and then it can bind. For example, when you have a cobalt or copper, then they oxidize olefinic and benzylic substrates to their epoxides. So, epoxides can be found, for example, okay, this compound with oxygen from air in presence of one aldehyde, that is sacrificial isobutyraldehyde, sacrificial, you can get in very good yield epoxide. Okay. What is the yield? Yield is quantitative. Quantitative. Okay. So, almost quantitative yield you can get. So, therefore, there are many other reactions, I am going to talk about that, and in a suitable cases that I showed you earlier, with the pyrazole and other cases, there more than one metal ion can be inside. So, that means in a cryptand we can put one metal, depending upon its structure we can put mononuclear cryptate, that is known as, we can put dinuclear cryptate, and we can put trinuclear cryptate as well. So, different types of different numbers of metal ions can be put inside the cavity, and that depends upon the length of the cavity, its environment, so on and so forth. So, thank you.